Thank you for the very generous introduction, and may I also contribute my thanks to all the organisers and all the effort they've put in to make this meeting a success. I think, well, certainly up until now, the standard of talks has been superb, and I've enjoyed myself very much. Now, the title I gave was a little bit formal. I prefer this slightly more informal one that's on the board. When I was first sent the schedule about a month or so ago, I thought I would be the very last speaker in the meeting, although I've been assured that the talks that come after me can be viewed as part of the combinatorics meeting, which is continuing. So in a way, I'm allowed to think of myself a little bit as the last speaker. So I chose something that would be a talk that would be fairly light, not too technical. It's Sunday lunchtime, you're all tired from your hard work, and you can see it's sunny outside, so you don't want to sit here and have to struggle to understand things too much. So I'm going to begin pretty gently with some simple calculations, and I hope that they'll lead fairly naturally into something a little bit more surprising. Some of you will know the material very well, but I hope others will find it a little bit surprising. Now, what is the talk actually about? It's about convex domains, which turn up a lot in analysis, combinatorics, and theoretical computer science. And it's about looking at where their volume or their mass, if you think of them as solid objects, where it sits within the space occupied by the body. And one's initial feelings are often not very accurate about how this happens. So I'm going to begin with the simplest possible. No, I'm not. How do I? All right, let's use this. With the simplest possible convex domain in Rn, the Euclidean ball. And let's just begin by calculating the volume of the Euclidean ball, a little bit roughly. So what if Vn is the volume of the ball of radius 1? What is it? Well, when you take the ball of radius 1 and slice it down the middle, you get a ball of radius 1, but of one dimension lower. So that has volume Vn minus 1. And then you can calculate Vn by integrating the areas of all the slices parallel to that slice you took. And of course, you have to scale them by the radius, which is root 1 minus x squared, if your distance x away from 0, raised to the power n minus 1, because that's how volume scales in dimension n minus 1. So you have an inductive relationship, an exact inductive relationship between Vn and Vn minus 1. And then when you do this little integral, or you approximate this little integral, you get something like 1 over root n. It's about root 2 pi over root n. This looks rather like a Gaussian density, this high power. And so if you want to calculate Vn, roughly speaking, what's going to happen, each time you go up a dimension, you multiply by root 2 pi. So that means you're going to get root 2 pi to the n. And then on the bottom, you divide by root n. So after n steps, you're going to get roughly root n factorial on the bottom. And n factorial is n over e to the n, plus some other stuff. And so you're going to get e over n to the n when it's the other way up. Yeah? So roughly speaking, I mean, it's rough, but it's really not too rough. The volume is about the nth power of root 2 pi e over n. In other words, the volume is extremely small. So the Euclidean unit ball has tiny, tiny, tiny volume, which already for some people is a little surprising. Okay? You think of a cube, which has side 1, it'll have volume 1. That's, in a sense, how we normalize Lebesgue measure. We claim that a cube of side 1 has volume 1. So you feel that something of size 1 has volume 1. But of course, this is completely false. The cube, when you look at it like this, is only width 1. But if you look at its main diagonal, if you take the opposite corners of the cube, suspended as if it were on a lathe, something that you were turning to carve on a lathe, of course, this distance is root n. The distance between opposite corners is root n. And the point is that distance is the typical one. What you see when you look at it in a square on is very rare. You're looking at a very special direction. The typical width when you look at it is root n. So an object of volume 1 is typically of size root n, or of course it could be much more, but at least root n, in almost all directions. And in particular, if it's a ball, it's the same width in all directions, and it's almost root n. Okay, so I am going to talk about sets of volume 1, so rather than size 1 and volume minuscule, vanishingly small. I'm going to talk about sets of volume 1. And I'm going to think of them, in fact, as having a probability measure on them, which they inherit from Lebesgue measure. In other words, they inherit the Lebesgue measure from the space, and that becomes a probability measure if the thing has volume 1. So what is the volume of the Euclidean, what is the radius of the ball of volume 1, the Euclidean ball of volume 1? We have to rescale by the reciprocal of that thing whose nth power we had before. And so we end up with radius root n over 2 pi e. So in other words, if the volume of the unit ball is tiny, then you need big radius to have volume 1. So the ball of volume 1 has radius about root n. It's very big, if n is big. And I've said here, where is the volume located? Now, obviously, that's a pretty vague question. I'm not going to answer that question. What I'm going to do is show you some parts of the ball which have large volume. In other words, I'm going to give you some answers to where it's located, rather than claim that this is a question that makes sense. Okay? I'm going to say, well, there's a lot located here, and there's a lot located there, and then you get a picture which will perhaps be different from the one you already have. Everyone okay so far? Ball of volume 1, big fat thing. Good. Okay, so how am I going to describe first where the volume is located? I'm going to ask what happens if you look at the ball and you ask where is it located with respect to a certain direction. Pick a direction, say the first coordinate of space if you wish, and ask where is the volume located with respect to position in that direction. Okay? So I take my direction here is horizontal. I've got the ball of radius r. This r, remember, is about root n. And again, I slice down the middle, and that has a certain area. Now, because the radius is going up like root n, the n-1 dimensional ball of volume 1 is a bit smaller. So this section has volume a bit bigger than 1. Okay? It's a bit bigger than you need to have volume 1 in the lower dimension because the radius is going up with dimension. Okay? So in fact, this slice has n-1 dimensional volume about square root of e. Okay? I mean, you can do the calculation, it's not too hard. Now, where does the volume sit in this horizontal direction? Well, we already saw you take these slices. In order to get the slice, the area of the slice, or the n-1 dimensional volume of the slice at distance x, you have to multiply by the radius at that distance to the power n-1. So you have to multiply by this radius, which is root 1 minus x squared over r squared, to the power n-1. And that will give you the area of the slice at distance x. And then you can approximate this reasonably well by using the standard exponential approximation. Remember that r squared is about n, r is about root n, so r squared is about n. So you've got x squared over n, 1 minus x squared over n to the power n. So that's roughly e to the minus something times x squared. And that something doesn't depend on n. In other words, whatever the dimension, when you look at this ball and you ask where is the mass located horizontally, it's in the same place. It looks like a Gaussian, which doesn't depend on n. Right? So although the ball is growing, like root n, the place where the mass sits is just the same. It just stays where it is, okay? Horizontally. And it looks like a Gaussian, which is kind of nice, of course. We're analysts, or some of us, even the combinatoricists, know that everything is actually a Gaussian, so it doesn't really surprise us, but still, it's nice to just check, sure enough, the world is as it's supposed to be. So already, that's a little bit of a probabilistic feature of a high-dimensional object, although it's only one high-dimensional object, a ball. Okay, so there we are. There is a ball in high dimensions, big radius. When you scan across it and you plot a graph of the slices, the volumes of the slices, or the n-1 dimensional volumes of the slices, you get a Gaussian. This Gaussian has a radius has a variance which is fixed, independent of n. And of course, when n is big, that's tiny compared to the radius of the ball. So you see this spiky little Gaussian in the middle. And most of the mass of the ball lies in this slab of a fixed width, even though the radius is growing. Okay? Anyone not clear about the picture? So almost all the volume lies in a slab of fixed width, even though in high dimensions the ball is huge. So the length scale that the ball sees when you measure it with calipers is root n, but when you measure it with a scale, if you weigh stuff, the length scale is much shorter. Okay? Now, of course, this doesn't just happen in one direction, it happens in all directions. So the volume concentrates in this slab here, and it concentrates in that slab there, and that one there. It concentrates in every slab of a fixed width. So that means that all the volume, in fact, must lie altogether, exactly on the surface. Almost all the volume lies extremely close to the surface, right? If you multiply the radius by 1 minus 1 over n and take the nth power, you've multiplied the volume by 1 over e. So you've gone down, you've got half the volume, and that's multiplying the radius by 1 minus 1 over n, but the radius is root n. So actually the thickness of the shell that contains most of the mass is 1 over root n. It's actually thin, even though the radius is big. Okay? And yet all the mass lies in any slab that you pick. Well, of course, the point is that the slabs meet on the surface. In high dimensions, they don't just meet in the center. The slabs meet on the surface because you're in high dimensions. Right? There's not a contradiction. It's just something a little counterintuitive. Right? Everyone clear about what I mean by slabs meeting on the surface? Good. Excellent. Right. So, very, very simple, just calculations, and yet some people are at least playing along and pretending that they're surprised, which is nice. Okay, good. Okay, let's move on to something which is a bit more sophisticated. This is the Brumm-Minkowski inequality, and this I think of it as the fundamental relationship between volume and the linear structure of space, of Rn, Euclidean space of whatever dimension. And what does the Brumm-Minkowski inequality say? It says something about what happens to volume when you add sets. What does it mean to add sets? Well, it means pretty much the only thing it could. You have two sets, A and B, and you form a new set by picking any point you wish from A, any point you wish from B, adding them together, and then looking at all the points you get that way. So A plus B is the set of all points of the form little a plus little b, where A belongs to A and little b belongs to B. Okay? So you form a set that way. And the picture you have in mind is this one I've drawn. So let's say your set A is a red square. I mean, the colour's not so important, it's just to help you see it. So it's a square, and you're going to add to it a disk. B is a disk, okay? Let's say centred at the origin. So how do you add the two sets? You put a copy of that disk at every point of the square, and then you sort of join them all up. You take the union, okay? So what you end up with is this square with the corners rounded off, which is a bit bigger than the red one, the blue one, in other words. Okay, so the blue thing, the whole blue thing is the sum. The red thing is the whole square. It's not just the boundary; it's the whole square. You add this disk, and you get the whole blue thing, filled-in blue thing. Yeah. So everyone got the picture of addition. It's very simple. And Brumm-Minkowski says when you add sets, the volume goes up in a strong way. Okay. You don't just add the volumes, you do much, much more than that. And there are a number of ways of writing it. The one which I like best is this one, because it's dimension independent, which in a way is odd, because most of what I'm trying to convince you of is that interesting things happen when the dimension grows. And yet I want to use a phenomenon or a way of writing the phenomenon which is dimension independent. But it turns out that for many purposes it is just a bit easier to use this formulation. So it's equivalent to the usual formulation, but it's a little bit simpler. So what is meant by this? So I'm going to add two sets, but I rescale them first by convex multipliers, lambda and 1 minus lambda, things that add up to 1. So I rescale them a bit and then add. And what happens when I do that is that the volume is at least this geometric mean, or weighted geometric mean of the original volumes. So of course, if lambda was 0, I would really just be adding a single point. Lambda times b would just be a single point, 0. So it would leave A unchanged, and there would be equality. Agreed? I would have A on both sides, if you like. So what happens is it's a kind of a concavity property of what happens in between A and B when you combine these sets in some sort of averaging. It means that the volume is big in the middle in some sort of concave way. Okay? So this is the Brumm-Minkowski inequality. And as I say, to my mind, this is the fundamental relationship between volume and the linear structure of space. Okay, now, at the bottom there, I've written what happens when lambda is 2, and that's the only case I'm going to use today. So when I average these two sets, I shrink them both by a half and add them, or if you prefer, I take the average of each point in A with each point in B, and then take the union of those. Okay? Its volume is at least the square root of this product, volume A, volume B. And I'm going to show you that this has an implication for the Euclidean ball, which is a bit surprising. And this is going to be a deviation inequality. Those of you who are familiar with them will have anticipated that, because I've said, suppose A is a subset of the ball, which has half its measure, which is what people would think of as a set that is sort of ripe for extension within these deviation inequalities. So the situation is this. I've got a ball, and I take a subset of it which is half as big. So the ball has volume 1, A has volume a half inside the ball. And I now extend it a bit. I look at all the points which are fairly close, distance t away. Okay, so I look at lots of points close to this set of size a half. And then everything else I call B. All right? So far that's all I'm doing. Now, the point about deviation inequalities is the idea that what's left, what this B is left over, should be very small. So the idea is that a deviation inequality exists where, as soon as you filled up half the set, you're almost everything. You're close to almost everything. Okay? And I'm going to demonstrate that this happens in the Euclidean ball just using this Brumm-Minkowski inequality. So I've got two sets, A and B. I can add them. I can take their average. I can take A plus B over 2. I can apply Brumm-Minkowski inequality to something, A plus B over 2. I do it. And what do I get? Well, I get this inequality, and then I say if I know the volume of A is a half, I get a statement just about the volume of B and related to the volume of A plus B over 2. So I have an upper estimate for the volume of B. Yeah? My claim is the volume of B is very small. And I'm going to show that the volume of A plus B over 2 is very small, and that's going to do the job, right? Now, those who are familiar with Brumm-Minkowski before they saw this argument, most of them actually will have seen this argument already, but I was certainly in the position of thinking, well, this is a little bit strange. How can this possibly be useful? Because the whole point of Brumm-Minkowski is that it tells you that when you add sets, they get bigger, quite a lot bigger, which is what I've written down. I mean, the volume of A plus B over 2 is bigger. So how can it possibly be useful to estimate the size of this tiny, tiny b by this thing involving A, which is huge? It seems mad, completely mad. But because of the shape of the ball, it turns out we can do that. So what are our data? Our data are, of course, A has size a half, and if you pick a point in A and a point in B, they are distance at least t. Those are the data we're given. Agree? And I'm going to use the second piece of information. Okay, so let's do that. What do? I draw a picture, and I accidentally write epsilon instead of t. And I really mean it was an accident. It's meant to be t. Okay, so these 2 points are distance t apart. But they're in a ball, and a ball is round. It's very uniformly round, convex. And that means that if you take points a fair way apart and average them, the average gets pulled in from the boundary. It can't stay close to the boundary because of the curvature. Right? So if you know that they're distance t apart, and you know the radius of the ball, which is r, you get an estimate for the size of the average. It's r times something a bit less than 1, because you've pulled in the average from the boundary, yeah? Because the points in question were separated. Anyone not clear about that? Okay, so we pulled the thing in, and that means that A plus B over 2, this set of averages, is inside a smaller ball. A ball not of radius r, but of r times 1 minus r squared over t squared over 8r squared, where it is, right? which is kind of strange. Right? You've taken these two sets, right near the boundary, and then when you average them, somehow it can never go near the boundary. It's pulled in. Okay, but that's fantastic news, because if this thing is contained in a smaller multiple of the ball, then its volume is much, much, much smaller than the volume of the ball, because we raise to the power n. This is the power of the dimensionality. We don't use it in the statement of Brumm-Minkowski. I use this dimension-independent form, but here we get to use it, and it has an enormous effect. We multiply, we have this, the volume, it's actually the volume of a plus b over 2 squared, because if you remember there was a square root in the Brumm-Minkowski. So we take the 2nth power of this factor, and it gives us something like e to the minus t squared, because again, this r squared is n, and we've got power n, and so we get e to the minus t squared. So that means you take a set of size 1/2 in the ball, you move distance t, what's left is very small, at least if t is 5 or 6 or 10 or whatever. So in other words, the length scale that is seen by the calipers is root n, by the measuring stick, but the weight sees only a length scale of 1. If you're a distance 1 or 2 away from 1/2 the thing, you've got everything. There's almost nothing left. And of course, to begin with, we saw this for a hemisphere. We said, here's the center, and as you move away from the center, the volume decays like a Gaussian, e to the minus t squared. Now we see that not only is this true if you start off with a hemisphere as your A, but with any set of size 1/2, any A of size 1/2. And this is a typical deviation principle within probability theory. Here it's a geometric deviation, but the idea is exactly the same, that once you've got half the space, whatever is close to it fills up almost everything. And this is a very powerful fact. Gideon Shechtman came up with a very nice way of saying this. He said the measure and the metric don't match. So the metric sees things at distance root n, but the measure sees everything on a length scale of 1. Constant. Okay, they don't match. Okie doke. Now, I want to talk very briefly about one more convex domain, one more concrete convex domain, which I already mentioned, the cube. And then, once I've done that, I will start talking a little bit more generally about arbitrary convex domains and what we do know, what we don't know, what we think may be true, what we don't. So I just want to relate the cube a little bit to what we've seen already. So the cube, I said the Euclidean ball was the simplest convex domain. In a sense, you could say the cube is actually simpler in a way. Certainly its volume is simpler to calculate. If its side length is 1, the volume is 1. It's just a product. Okay? Now, because it's a product, the indicator function of the cube is actually the density of, or the joint density of independent random variables which are distributed uniformly. So in other words, if you look at the coordinates of a point in the cube, the coordinates are, of course, random variables. Each one is distributed uniformly on the interval. And because the cube is the product, these coordinates are independent as random variables. Okay, this is the typical picture of independence as being about multiplying. Okay, so if you look at the coordinates of a random point in the cube, they are IID, uniform random variables. And that means that if you take the cube and you do what we did before, you take opposite corners and you suspend it like this, as if it were on a lathe, right? Everyone know what a lathe is? This thing where you make wooden, table legs. Okay. So you suspend it like this, and you sort of spin, you can spin around. But I'll draw it. Why don't I draw it? Stupid. There. So there is the cube, suspended on a lathe. Okay? You've got these little things, and you plug the corners of the cube into these things and hold it. Okay, so there it is, width root n. What was I going to say? Oh, yes, right. So what happens if you look at the volume as you scan across like this? Now you're suspending it with the corners. Well, what you get, so the distance in this direction, is just the inner product of the vector, x1 up to xn, with the diagonal, the direction which gives you this, this main diagonal of the cube. So it's just what you get when you take the inner product of x1 up to xn with 1 over root n up to 1 over root n, and that's just the normalized sum 1 over root n sigma xi. In other words, It's exactly what appears in the central limit theorem. So we have IID random variables, we add them up, we renormalize so that the variance stays the same, which means there's a chance that what we get will be identifiable because we're not letting it spread out too far or crushing it too much, and it becomes a Gaussian. This is the central limit theorem. So this is exactly the situation we had in the ball, where when we scanned across the Euclidean ball, we saw a Gaussian. It was a Gaussian of fixed variance, independent of the dimension. Similarly here, we get a Gaussian of the same variance as the uniform distribution, which of course is, again, independent of n. So we get exactly the same phenomenon for the cube, but of course not in every single direction. If you take these special coordinate directions, what you see is a uniform random variable. But if you go to the standard proofs of the central limit theorem, or standard generalizations, you will see that in almost all directions for the cube, you will get a Gaussian. Only the very special directions, which are coordinate directions or close to them, will give you something different from a Gaussian. So we're in exactly the same situation as for the Euclidean ball, except not quite in every direction, but in all but a tiny proportion of the directions, you get a Gaussian cross-section. Okay? So in that sense, the cube is like a ball. And we know that from stuff that was already known. Central limit theorem, probability theory, absolutely classical probability theory. What about deviation? What about this extension to arbitrary sets of size 1/2? Do we have a deviation principle for the cube? The answer is yes. In fact, there are many different proofs of it now. All kinds of logarithmic Sobolev inequalities, transportation inequalities, many, many ways of doing it. But one particularly nice way, one way that I'm very fond of, was found by Pizier. So long before this question, it was understood that there is a deviation principle for Gaussian measure. And there are also many, many proofs of that. One way to prove it would be to use that Brumm-Minkowski argument that I gave you, but apply it to Gaussian measure. That was not historically the first, or probably not even the fifth proof, but it's a way of doing it. And the reason it works is that the Gaussian is rotation invariant, just like the ball. So if you go and try and use Brumm-Minkowski, you can prove deviation for the Gaussian, and it works because the Gaussian is like a ball in the sense that it's round. But the Gaussian also is like a cube in the sense that it's a product. Okay? And so what you can do is you can take the Gaussian measure and you can map it to the cube in a measure-preserving way just by mapping each coordinate separately. The coordinates are independent in both cases, so you just map them separately in the obvious way. You just, here's the measure, you just kind of squash it so that it fits perfectly in a measure-preserving way onto the interval. And because this is essentially a one-dimensional thing that you're doing, or lots of different one-dimensional things you're doing, it becomes trivial to check that this is a Lipschitz map. You only have to look at one coordinate at a time, in a sense. And because it's a Lipschitz map, it enables you to transfer the deviation for the Gaussian to a deviation on the cube. So you get exactly the same principle as we had for the ball. If you take half the cube, any half of the cube in volume, everything, or almost everything, is rather close to it. Okay. Good. Okay, so now we come to general convex domains. Do they look like Euclidean balls? Well, obviously not. Why? Well, one problem is you could take something of volume 1, which was incredibly thin and very, 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 very long. And then, of course, it would really look as though it was one-dimensional, like a line. And so there'd be no possibility of saying, because the dimension is high, this looks like a high-dimensional Euclidean ball, because it's not high-dimensional, it's just a line. In other words, of course, you can put lines in Rn. That doesn't make them n-dimensional. So you've got to avoid the problem of having something which is really of lower dimension. So you've got to allow yourself an affine transformation or a linear transformation. So all rectangles you transform into squares. All cuboids you transform into cubes. All ellipses you transform into circles, and so on. Okay? But modulo that, we keep the shape. Apart from that, we keep the shape. And the transformation I'm going to use will be one that makes the inertia tensor of the resulting object a multiple of the identity. So what does that mean? So in other words, you pick any axis, you try to spin this object around the axis, you have a moment of inertia, and what we want is that that moment of inertia will be the same whichever axis you pick. Right? A kind of uniformity of direction, so the thing is as round as it can be. Can't be long and thin. Something long and thin would have a huge moment of inertia about here, but a tiny, tiny one about that. Okay? I can't really do Robin Williams, can I? Okay, so the formula we want is this, that whenever you take a direction theta and you integrate this square of the inner product against a random point in k, in other words, you average over k of the square of the inner product, you get some number independent of the direction, okay, as long as it's a unit vector. And when that happens, when we have a set which we've transformed in that way, we always can transform our set that way, it's very easy to check. When we have such a thing, we call it isotropic, so same in all directions. That's roughly what isotropic means. Is everyone clear about the picture that I'm creating? So I'm trying to make the set as round as I can, but without changing its real shape. So rectangles become squares, not circles, but they're the same shape. I'm only laying out a linear transformation, but they're as sort of equal as they can be in all directions. Yeah? Anyone not clear? Good. Okay, so I've got an isotropic set, volume 1. I think of it as a probability space. I have Lebesgue measure restricted to this set, total mass 1. This is a probability space. If I have a function on this set, then it becomes a random variable, if it's a real function, or a random vector, if it's a vector value function. And I'm going to start looking at the simplest one, in which the value of this function of the point is just the point. In other words, I just pick a randomly distributed point, a uniformly distributed point within the set. Okay, that's the simplest random vector I can put on this set of volume 1. And the isotropic condition tells me that whenever I look at the marginals of this random vector, so I take the inner product with a direction and look at the random variable I get, the one-dimensional random variable I get, this thing has a certain variance, and the isotropic condition says all those variances are the same. Of course, in the case of the ball, that was obvious because of symmetry. In the case of the cube, it was also true because of the property you learn in elementary statistics that when you add up independent random variables, the variance of the sum is the sum of the variances. So in other words, the variance doesn't change in a complicated way with direction, it just depends on the things you're taking the inner product with. Okay, so here we have the situation. We have this fat set. We have a random point in it, and all its marginals have the same variance. Okay? And so we can now ask, do we have the same properties as for the ball or for the cube? Are these marginals all Gaussians? Almost all Gaussians, like the cube. Do we have a deviation inequality? Is it true that whatever set you pick inside this convex domain, if it fills up half the domain, then it's close to almost everything? Okay, we can ask those questions. And indeed, people did. Before I actually remark who it was, let me just point out that once we have this isotropic condition, we know the average radius of our set, the average radius of a point, of our random point in the set, because we can write the square of x, the square of the length of x, as a sum of the squares of the inner products of x with an orthonormal basis, and we apply the isotropic condition to each ei, so we just get n times this L squared. In other words, the root mean square norm, the average in the root mean square sense, Euclidean norm of a point in this K is root nL. So the volume is 1, root n times L is its sort of typical radius. Okay, so as for the ball, we had root n over root 2 pi e, so we get that L for the ball is 1 over root 2 pi e, which is about 0.24. And for the cube, you can calculate easily, it's 1 over root 12, 0.288. Okay, so these L's for the cube and the ball are about the same. And then the typical radius of the ball of the point in the set is about root n times L. Okay? Right, so that now enables me to write down the 3 conjectures that people made. So in the 80s, Bourgain conjectured that this L, this coefficient, when you look at the inertia tensor, you look at what multiple of the identity you get, in other words, this number that appears in the typical radius, that it should be uniformly bounded. It's very easy to show that it's at least a certain amount. It's at least as big as what you get for the Euclidean ball, because you can't pack stuff better than the Euclidean ball, pack it closer to the origin than the Euclidean ball. But he conjectured that there's an upper bound. About 10 years later, Kanonlovas and Szymanowicz conjectured that there is a deviation inequality for all convex domains on the length scale of this number L, whatever it is. It was not known whether it was bounded or not, but whatever that L is, the idea is, it is the correct length scale for this convex domain, and there should be a deviation inequality on that length scale. So you take half the body, you move L away from it, you pick up most of what's left, you move another L away from it, you pick up almost all of what's left, you move another L away from it, you pick up practically everything of what's left. Okay? So length scale L, deviation on that length scale. That was the conjecture of KLS. And about the same time, I conjectured that there should be a central limit theorem for all convex domains, which you've made isotropic, made as round as you can, in the sense that in most directions the margin will be Gaussian, just as in the case of the cube. Okay? These conjectures were not exactly independent. I mean, well, 10 years between them, they couldn't be quite independent, but even the two that were close together, we were sort of talking together, talking at the time. So they're not quite independent, but this is a more or less accurate account of what happened. And I'm going to tell you something about what has been discovered about these conjectures in the subsequent 20-odd years. Quite a lot has been discovered, although there is a huge amount left to discover, a huge amount we don't know, and that will emerge as I carry on. Now, the first remark is that it's very easy to see that there is a trivial estimate for L, which is root n. If I just ask you to fiddle around for a little while, you will come up with a way to prove that L can't be much more than root n, 2 root n or 5 root n or something. Okay, so that's the trivial bound. The conjecture is that L is bounded, independent of n and the domain. Now, Bourgain himself improved this root n to n to the 1/4 with some logarithmic terms, and I think eventually it got down to 1 logarithmic factor, and that logarithmic factor was then removed quite a lot later by Klartag, who combined his isomorphic slicing theorem. So this was a theorem about what happens when you calculate these inertia tensors, but for bodies which are similar to the one you've got. So instead of looking exactly at the convex set that you've got, you're allowed to modify it a bit and then calculate the inertia. Okay? So he combined that with a delicate estimate of Paouris, which is written below. And putting those two together, it was actually rather easy to see that you could remove the log n term in Bourgain. And what does Paouris' estimate say? It is a bit like the KLS. So remember, the typical radius is root n times L. And KLS says that almost all the mass is close to root n times L, because half is inside and half is outside. So most of it is going to be rather close to that dividing radius. And Paouris says if you go a fair bit further, say a multiple of root nl, then not much is left. So it's in the same spirit as a deviation inequality. If you go out about root nl, you pick up about half the mass, and you go twice as far, 3 times as far, the mass really does drop off rapidly. Okay? So it's in the same spirit, but it's not the same statement. I mean, it's definitely a weaker statement. Okay, so that's what is known really about Bourgain's conjecture, not much more than that. Well, okay, no, that's not quite true. Quite a lot is known about Bourgain's conjecture for specifically shaped convex domains, so convex domains that come from normed spaces, which are the unit balls of normed spaces with particular properties, but in general, not much more is known than this. Okay, I said, again, the average norm is about root nl, so the average radius of a point in our domain is about root nl. And a couple of my students and I pointed out that if you have a kind of weak law of large numbers, which says that if most of the mass lies fairly close to this, not nearly as close as predicted by the KLS conjecture, but fairly close, then you will automatically get this central limit phenomenon holding. You'll automatically see Gaussians in most directions. And in fact, it would have been possible to deduce this using some properties of convex domains that were pretty well known from earlier work of either Diaconis and Friedman or Sudikoff and von Weizsäcker, where they also proved that a kind of weak law of large numbers implies a central limit theorem, but with much more general conditions, but not surprisingly rather weaker estimates. I mean, convexity is a condition which gives you a very precise sort of shape to your probability measure, so it's not surprising that you can get much more accurate measures of how close you are to Gaussian, but of course it's much more specific because you have a convex region rather than just a much more general measure. So in principle what we did is a sharpening of a special case, but the methods are so different that I think it's more reasonable to think of these as just being rather different issues. It depends how you feel about these sort of questions. Okay, so central limit problem holds if you have this sort of concentration of mass in a shell. Okay, if most of the mass of the domain lies in a shell of course of the radius root NL, the typical radius. I mean, if it's going to be anywhere, it's got to be there. Now it looks as though this is kind of a silly observation. I mean, if it looks as though what you're saying is, well, the mass lies in this shell, so roughly speaking, the body looks like a shell, and for a shell, we know the central limit thing. We know that for a Euclidean ball, the central limit thing works, so it works for a shell, because we could just apply the same sort of argument just to the shell instead of putting it another way, we know the Euclidean ball basically is a shell, so if it works for that, it must work for a shell. Okay? So it looks as though this is kind of a silly statement. If the mass lies in a shell, we have a shell, of course we have central limit. But that's not what's happening. If the mass lies mostly in this shell, it still only occupies a minuscule fraction of it, e to the minus n. Right? And that means it needn't look anything like the shell. What matters is how the mass is distributed within the shell. Okay? So we need to invoke the isotropic condition to show that it's distributed kind of everywhere, and then convexity to show that it sort of it joins up in a way, and so on. It's not just saying it looks like a shell. It doesn't look like a shell. And as I mentioned, the deviation conjecture of KLS, Lovas and Szymanowicz, is actually much, much, much stronger than the hypothesis we're making here, this shell hypothesis that we need. In other words, KLS certainly implies the central limit problem. Right? I mean, but by a huge margin. It's much stronger than you need. So that's one of the relationships between these three conjectures. Okay. For both the central limit problem and KLS, the length scale is this number L, this measure of the variance of the marginals of this uniformly distributed random vector. So both KLS and the central limit problem take for granted that the length scale is L, whereas Bourgain's conjecture says we want to know how big L is. It says L is not too big. So they are, in a sense, sort of separate. Two of them say, whatever L is, we'll use it, even if it's big, if it's not. Whereas Bourgain says, I want to know how big L is. Okay? So they appear to be sort of independent. Now, the central limit problem was actually solved. So of the three, it's the only one that's been solved. There were a number of special cases that were known, special kinds of bodies and so on, but it was solved in full generality by Klaartag, and then very shortly afterwards, Pauris and Fleury and Guédon produced a very different proof. And so we know, in fact, and actually both these proofs go via showing in some way or another that most of the mass does lie in a shell. So they make use of this phenomenon, although, I mean, that would have been kind of automatic from the way the proof went. So indeed, we know that the mass concentrates in a shell which is at least smaller than its radius. It's not a thin shell, but it's at least a bit smaller than its radius. And therefore, we know that in most directions, the marginals are Gaussian. So this is one sense in which high-dimensional objects, convex domains, genuinely have a probabilistic character. I mean, they have Gaussian marginals. Right? What more probabilistic feel could you have than Okie doke, so that problem has been solved. And here is the sort of picture. This red thing is a convex domain. This picture of convex domains was popularized by Millman. And the way you see it is this. The red thing is convex, and then most of the mass lies inside that ring, inside that shell between the two circles. And my motto for this picture was something like this. I coined a sort of motto. This may not look like a convex set, or the set may not look convex, but this is how convex sets look. Okay? They look spiky. In high dimensions, convex sets have a kind of solid core, but they look very spiky. And this is even true of the round one, and the Euclidean ball. Even the round one looks spiky. Right? So it's not that the core, the core is round, but the core is also spiky. Right? So the picture is a little odd. Okay? So you've got this core where all the mass is, but if you look in a given direction, you don't have to go very far before the mass has all disappeared, and then everything else is just these little tendrils going off. Right? But that's in all directions. Right? So it's kind of spiky in all directions, even though it's round. Right? So this is the picture. And at a certain level, we actually know this. Right? We actually have this central limit problem. We have this mass lying in a shell, not a thin shell, but at least a shell which is not quite as big as the actual object. I mentioned that the KLS conjecture and the central limit problem kind of sit over here, and Bourgain's conjecture over here, because over here we assume the length scale is L, whatever it may be. If it's big, if it's small, or maybe constant, or if it's root n or n to the quarter, whatever it may be, L we take for granted if we're in the central limit problem or the KLS conjecture, whereas Bourgain says we want to know that L is small. So these are sort of independent, at least formally. However, informally, our picture, of course, is the opposite, that these conjectures are somehow fighting against each other. Right? Bourgain says that L is small, but KLS says that L is big enough that things concentrate at that length scale. So it's forcing L to be big, right? Formally, they don't, of course, formally they're not contradictory. Or they could both be true, but they appear to be saying opposite things, right? Bourgain says L is small in a very simple way, it's just L is not too big. But KLS says L has got to be sort of big because the thing concentrates at length scale L. So L can't be too small because the thing can't concentrate in too small a length scale. So they appear to be kind of opposite to one another. Great, does that make sense to everyone? Yeah? Good. Okay, another way of saying it is that Bourgain's theorem says that linear functions don't deviate too rapidly, whereas KLS says that they are the worst, that no other function deviates worse than a linear function. Okay, so again, there's a sort of conflict between them. Okay? So it's a little odd that one implies the other. KLS implies Bourgain's conjecture. In other words, if the volume concentrates at length scale L, L can't be too big. It looks like concentrating at length scale L forces L to be big, but in fact it forces L to be small, which is kind of weird. Well, yes. With hindsight, of course, weirdness can usually be argued away. We are mathematicians, we're skilled at making arguments. So underneath I've argued it away. So what have you got? You've got this radius L, and you know that most of the mass sits pretty much bang on that radius, spread around kind of uniformly because the thing is isotropic, so it's got to be kind of the same in all directions. And you also know that it's convex, so you can fill in all the stuff from all this stuff that's at length scale L. But of course, if it's too far away and you fill it all in, you're going to end up with too much stuff because you're only allowed volume 1. Right? Did you get the picture? That if you tell me that all the mass is really, really there and spread around, and that you've got everything that is a convex combination, you're just going to get a whole load of stuff. And the bigger L is, the more stuff. And that, of course, will then violate the fact that, or the hypothesis that the thing has volume 1. Obviously, that's not an argument. You can't turn that into an argument. It's kind of weird. But with hindsight, you can sort of see how If you have convexity and this isotropic condition, then concentrating at length scale L means L can't be too big. And in fact, that is the case. So this was something I proved about 10 years ago. Okay, just to finish off, let me remark, I haven't actually told you what the KLS conjecture really says. I've been a bit vague about it. So just in case you wanted to think about this further, I thought it would be a good idea to say exactly what it says. So the KLS conjecture is a Poincare inequality. It's a conjectured Poincare inequality, or if you prefer, an estimate for the spectral gap of the Neumann-Laplacian on this domain. You can write it this way, that the integral of the square of the gradient of a function is at least the integral of the square of the function, provided that function is orthogonal to the constant function, which of course is an eigenfunction of the Laplacian. In other words, provided S has integral 0, right? Provided its average over k is 0. And you'll notice, and this makes it in a sense even clearer, the constant in this inequality has this L squared on the bottom. So KLF says you have an inequality like this, which appears to suggest that L is large, because it's on the bottom, on the downside of the inequality, but in fact it implies that L is small. Right, that's the previous slide. Finito. Where C is universal, of course, yes. Not independent dimension and the domain, yeah. Okay, now it's finished.
He lived up to my expectations. Are there any questions or comments?
Well, you spent time explaining how a convex body is a random experiment, right?
Yep.
You have the converse way given a random experiment. Where does it come from, convex body?
No idea. Absolutely no idea. I mean, the question might be, suppose you pick a kind of a natural random. I mean, obviously some experiments don't, but you might say, suppose you pick a natural one with the kind of properties that you're used to. Is it actually a bit like a convex set? Because the answer is, well, in one trivial sense it is. If you have a central limit theorem, you know that the measure is a product measure which looks like a ball or a Gaussian. Well, there you are. So in a sense, the answer is probably, if you can say anything about it, it probably does look like a convex thing. But I'm not sure that that's really something that you would want to prove, because it's not telling you anything. Maybe that's an answer.
If you take your different convex sets, for example, your sphere and your cube, and you renormalize them as you did, so they have the same inertial structure, then they all define measures on RD.
Yeah.
How much is known, well, I'm sure you know, how much is known about the structure of that space of measures? For example, the distances between measures. If I just take the cube and the sphere, what is the distance between those measures? Then you say it's total variation or any other. I mean, there are lots of different ways you can think of that.
Okay, people have thought about transportation distances between these measures because they are, roughly speaking, equivalent to the questions I asked, and therefore not, in most cases, the answer isn't no. Frank might know. Do you have any suggestion as to what's been done in addition to that? No? Okay, good. Don't feel too embarrassed then. So that's my answer.
Right. Okay.
Transportation is sort of understood, except that it's not understood, because we understand it's something too difficult.
Any other questions or comments? Yeah.
So you mentioned a couple of values you found. I think it was 2.2 for the cube and the ball.
Yeah.
Are there any, do you know if there's a largest one that we found so far?
So the conjecture, of course, is that they're bounded. So if you found the largest one, you'd become famous, or at least you would to Bourgain, which is good enough.
Well, I mean, the largest currently known.
The largest currently known, I think, is the cube. So 0.288, and it's not far from the smallest, which is 0.242. So, of course, we feel rather embarrassed about this. I mean, they look practically the same, and we still can't prove that it's bounded. So it is a bit embarrassing, I have to say. So when I say largest, I mean largest symmetric. If you want a non-symmetric, you can get something bigger like the simplex, but not much bigger.
which case I think it just remains to thank Keith again, and some others